Good morning, everyone. My name is Ayumi Manawadu. So today I'm going to present a part of a research myself, Dr. Haifeng Wen, and Dr. Pijong Shao has been working on for the past 3 years. So it's on freeze-thaw durability of concrete-to-shotcrete interface bonds in tension and mode 2 fracture. So this was funded by WashDOT and tried yearly. So let's start. So shotcrete is nothing but concrete sprayed at a very high velocity. And due to the high impact force at the point of application, shotcrete sort of compacts itself. So therefore, it does not need any external vibrations or formwork, a lot of formwork for that matter. Therefore, shotcrete is very popular when it comes to overhead and vertical concrete repairs, as you can see in the figure. But then we now have a concrete or a concrete substrate which is already hardened, and we place a fresh shotcrete layer on top of that. So there's a material mismatch between the two layers, and therefore the interface between the shotcrete and concrete is usually very weak, and it is susceptible to damage. So this project was focused on this interface bond. Also, there is another problem. Usually, these interface bonds are predominantly susceptible to shear type forces, but the most common test method for evaluation is based on tension loads. So that is one of the problems. So the most common test method is the pull-off test, pull-off tension test. You have the concrete substrate, and then you have the shotcrete overlay. You drill down to the concrete substrate, and then you try to pull it off. So depending on whether the concrete to shotcrete bond is weak or strong, the failure could happen at any point. It could happen at the substrate, it could happen at the overlay, or even at the bond. So every time when you measure the bond strength, you may or may not be measuring the bond strength. Exactly. So that is one of the problems with this test. Also, concrete, we know concrete shotcrete type quasi-brittle material, they have their inherent flows like microcracks, voids, etc. Those are not taken into consideration, which may lead to premature failure. They are not taken into consideration when it comes to strength-based tests. Furthermore, there is no standard method that highlights that take into consideration the short-term test results and predict the service life of a structure. So that is also another problem we are trying to answer here. So the objectives of this study, considering all these areas, first we were trying to come up with a new test method, more effective test method. To be precise here, we came up with a fracture-based test method. So it considers already existing flows in these type of composite structures. The second one was to use this fracture-based test method to characterize concrete-to-shotcrete interface bond. And then finally, to predict its service life based on the test results. So first of all, to develop this test method, we used, now one of the problems with the conventional pull-off test is it has a uniform cross-sectional area. It's a cylinder. So when you pull that off, it can break from anywhere. But when you have the interface area narrow, interface section more narrower, it's more likely to fail from there. So we pick something like a double wedge specimen where we try to optimize the wedge angle to give the highest ratio of fracture energy, mode 2 fracture energy to total fracture energy. That was our basic concept when we were trying to design this. And this was a very compact specimen. If you have seen fracture-based tests, they're little larger specimens. So we tried to come up with a compact specimen. And initially, we introduced two cracks as A note. So we did a finite element analysis to optimize this angle. And finally, we found that the 45-degree angle was the best one. So we designed it in that way. So then once the specimen was designed, then our target was to design the mold. So this mold, if you can see, there's a panel of 12 specimens. So you can cast it at one go without casting specimens separately. And first of all, we cast the concrete layer at the bottom in the lab, and then we took it to a site where ACI certified nozzleman did the shotcrete layer, because shotcreting, the quality of shotcreting depends on the skill of the nozzleman. So that's why we took it to the industry and got it done. So here, one thing we do usually to improve the bond between the concrete and the shotcrete is to prepare the concrete surface before laying the shotcrete on top of that. So there are different surface preparation techniques. For the characterization purpose, we chose three different techniques. One is to chip the surface, then to pressure wash, then to sandblast, and one control was left as cast. No preparation was done. Then we designed, so this also took a lot of effort to design the fixture for this test because it's a new test method. So to design this fixture, one important thing I would like to mention here is this fixture can do both mode 1 fracture type as well as mode 2 fracture type test with the same specimen. So that is one of its kind, because if you can see, mode 1 fracture is more like a tension type load, mode 2 fracture is more like a shear type load at the fracture. So this also took a lot of effort, but I will briefly talk about it. So then we used that specimen and the fixture to test the surface preparation techniques I mentioned before. So what we found is, like, if we use the fracture energy as the key characterization point, we found that the chip samples had the most mode 2 fracture resistance to the bond. So chipped followed by sandblasting and pressure wash, and ASCAS was the lowest. So as a comparison, we did conduct some tension test and shear test as well. But I want you to focus, tension test and shear test were done on uniform cylindrical samples, whereas double wedge specimens I introduced was used for fracture tests. And we found that the orange color bars in the second figure, the shear test characterization was more closely related to the fracture-based test characterization. But if you focus a little bit on the pressure washed and the sandblasted specimens in the second figure, you will see pressure washed specimens are better in tension than in shear, and sandblasted specimens are better in shear than in tension. So that indicates, depending on what type of a test method you use, your characterization may vary. So depending on your application, you might want to pick the right characterization method, or maybe a combination of them. And then we use the same test to characterize these specimen samples at 300 freeze-thaw cycles. So we did a laboratory freeze-thaw conditioning cycles, but then since these two are not comparable, I mean, you cannot compare directly tension test to fracture energy. I will use the relative durability factor as a comparison method. So it is nothing but fracture energy at 300 cycles compared to the initial fracture energy of a specimen, or tension strength at 300 cycles compared to initial tension strength. So when you do that, you can see that at 300 cycles, the fracture energy of chip samples have reduced to 91% compared to the initial one. But when you compare the tensile strength, it has reduced to 65% of the initial tension strength. Still, the initial values, initial patterns remain the same, but the reduction have some significant changes, if you see. And then, and if you can see, pay attention to the ASCA specimen, it has almost failed at 300 cycles. So it indicates that it's important that you do the surface preparation, and depending again on your application, you might want to pick the right surface preparation technique. Then what we did was, using the results, we tried to predict the service life of a structure at when the structure failed. That was the question we were asking. So we did a statistical regression analysis followed by a 3-parameter variable distribution based damage model. And then we found at which freeze-thaw cycle the composite structure would fail. And finally, using that, we found which year, like what's the number of years at which it would fail. So again, any equivalent number depends on how many freeze-thaw cycles per year. So it depends on what location you are speaking about. In Pullman, where it snows a lot, it's kind of is a higher number when you compare it with something like Seattle. So again, we did compare it with SeaTac and Pullman. So obviously, as you can see, a chip sample at which would remain for 42 years in Seattle, it would remain only for 6.5 years in Pullman. So this indicates the importance. And by this time, ASCA specimens would definitely fail. So it indicates that it's important you provide additional bond between, like a mechanical bond between the two, concrete and the shotcrete. It's very important when your area, if your building location is in a freeze-thaw prone area. So summarizing everything, we came up with this double wedge specimen, and then we used it successfully to characterize the bond between concrete and shotcrete. And we found that it is sensitive to the testing method as well as the texture of the sample. Chip surfaces were the best in both strength-based tests and fracture-based tests. And finally, we found that service life prediction models can be used to predict the service life in a different regions. So thank you so much. I'll be happy to answer any questions.
Very interesting presentation. I think probably for the sake of time, we didn't get the detail, but I was curious how you measure the fracture and you actually measure the spin part, because this fracture energy is size dependent. Because it's size dependent, the effect of the surface roughness will change size. So we want to measure the difference in the size. You need to get to a size where you know very that. So I wonder if you thought about development.
Yes, definitely. For this one, we use the usual way of measuring fracture energy. It's usually the area under the force displacement curve divided by, it's more like average, divided by the initial bonded area. But then you are right. So you need to think about like how the surface roughness works, we did not go into details at this point. So maybe it could be a future research, yes. Yes. Right. So what we did was, this was done for us by a contractor. So they actually used visual inspection. So they actually they make the surface, and then they actually use visual inspection as a kind of guide to decide whether this is good or bad. So we wanted to do it as close as possible to the industry, what the industry is doing. So yeah. Yes.
Yeah, for the chip processing, because it depends on the device, shipping versus your testing device. You see a difference.
I'm sorry, I didn't understand the question.
For the chip, the first one, you separate move.
Yes.
Certain direction.
Yes.
When you like shear the sample.
Right.
Which device you can shear perpendicular.
Yes.
Parallel.
So if you can see here, the chip surface is more like they do. Let me show you. Yeah. So in this one, it's like.
Okay.
Yeah. So this chip one has like. Yeah. So it's like a grid. Yeah. It's in one direction. Yeah. So we sheared it in this direction, but there are grooves in both directions. Yeah. Okay.
So yeah, thank you.